We're going to start on the examples on 5-1. And my first example is 5-1 on page 259. And we're going to construct a probability distribution for rolling a single die. So I know this experiment well. I know what the outcomes are. So this is what X is for. The X will organize all of your outcomes. So I know that I can roll a 1, a 2, a 3, a 4, 5, and 6. In order for this to be a complete probability distribution, you want to organize all of your outcomes and make sure that you have the whole sample space. Now on the bottom, I will describe the probability of each of those events happening. Well, the probability of rolling a 1 is 1/6. The probability of rolling a 2 is the same thing. So they're all the same probabilities. What I like you to notice is if you sum up all of the probabilities, just take 1/6 and add them all together. There's 6 of them. 6 times 1/6 is 1. And this is how you know that your probability distribution is complete. Now, this is a table. The book usually organizes tables as horizontally and as rows. What you will find very useful is in Excel, you will organize them as columns, because this is how you can tell that your first column is your x-axis and your second column is your y-axis, where you want to put probabilities, because this is exactly what you want to do in the histogram. I'm drawing this by hand, but you can easily do this on Excel. Your x-axis should be your 1, 2, 3, 4, 5, and 6. And right up there, you should have the 1/6. And notice that drawing a histogram of this probability distribution looks like you're using 1 through 6 as your classes, so they go on the x-axis, or better yet, the midpoints, because that's what it looks like. It looks like it's in the middle of your class. But instead of your frequency, you will have the probability. So we didn't cover this in chapter 2, although some of you have done some of the homework on the relative frequency distribution. Well, this is very similar, because what we have is we're going to organize our x's as our what looks like midpoints of classes, and the p of x, the probability, will go on your y-axis. And from this distribution, you can see that the shape of the distribution. So in this case, it looks like it's a uniform. So this is what we're going to have. My next example is tossing coins. This is example 5-2 on the next page. We are tossing 3 coins. And we are counting the number of heads. So my x, the outcome, is how many heads will I get when I toss 3 coins? Well, is it possible to get all 3 tails? Yes, so 0 heads. The probability of that event happening is actually 1/8. Now, in order for you to figure out this probability, this is where you draw a tree diagram and use material learned in chapter 4. So sometimes we will use some of this stuff in chapter 4. Other times it's a little bit easier, so you don't need to go into the details of chapter 4. But the reason why we did chapter 4 in the beginning of the semester is so some of the probabilities that we're writing down in later chapters actually make sense. So in order to figure this out, you draw a tree diagram. But for this example, I just want to give you those probabilities. So the probability of getting one of those 3 coins to be heads is 3/8. 2 is the same thing. and 3 is back at 0 because getting 0 heads or 0 tails should be the same probability. What you want to do is you want to be able to draw this, to draw a representation. This is a graphic representation. It does look like a histogram, but what you're treating is your 0 is actually the name of your class. So you have 0, 1, 2, 3, and then maybe I'll label this as 1 over 8. A little bit higher is 3 over 8. Way up there is your 1, so I'm not labeling that one. What I'd like to point out is I have one kind of bar, and then I have another one, and one back here. Notice this one looks symmetric. Let's continue. My next example is 5-3. A convenience store sells AA batteries in 2 per pack, 4 per pack, 6 per pack, and 8 per pack. The store sells 5 2-packs, 10 4-packs, 8 6-packs, and 2 8-packs over the weekend. Construct a probability distribution and draw a graph for the variable. So what I have is I no longer have the theoretical distribution, I have observational. So this one is a lot easier to figure out than the theoretical one, so there won't be any tree diagrams or any of the theoretical stuff that we've learned in chapter 4. This is observation. So what I need to do is I need to somehow write this down. So this is where the table comes in. So I'm selling I'm selling AA batteries, and they will either come in 2 per package. So this is my outcome is a 2 per package pack, I guess. A pack that has 4, a pack that has 6, and a pack that has 8. Now, before I tackle my probability, I need to write down the frequency. Because they didn't give me any probabilities, they gave me frequencies. They said the store sells 5 2-packs, so they're selling 5 of those. 10 4-packs, so you'll write frequency 10. They will sell 8 6-packs, so this is where I have the 8, and 2 8-packs. Now the first question is how many batteries or how many packages did they sell over this weekend or whatever they're counting. So you need to add, and you end up with 25 packages. Now if you have the total, you can now figure out the frequency. So if 5 2 packages out of 25, well, that's 5 out of 25, that's 0.2. So the probability of selling a package that has 2 batteries is 20%. Now what about 10? 10 divided by 25 is 0.4. So there's about 40% chance that a person comes in and they want a pack that has 4 batteries. The one that has a 6 has 8. So 8 divided by 25, this one happens to be 0.32. And the last one is 2 out of 25 is 0.08. So there's about 8% chance that a person comes in and they want a bigger pack, the one that has 8. Notice, if you add all of these up, 0.2, 0.4, 0.32, 0.8, you'll notice this is a 0.4, this is another 0.4, that's 0.8, another 0.2, so the sum is equal to a 1. So this is the important fact about probability distribution. And what I can do is I can draw this out. 2, 4, 6, 8. I don't need frequencies, I need probabilities. So notice the highest one is a 0.4, so maybe go by 0.1s, so 0.1, 0.2, 0.3, that way you can see the distribution. The first one is at 0.2, the second one is at 0.4, the next one is at 32, so that's about right there, and the last one is just under a 10% mark. So you can almost say that it's approximately symmetric, but really it is slightly skewed to the right. And if you have more than 4 entries to talk about, then you can actually discuss distributions and your findings. My last example in the book is example 5-4, and it's just a simple question of determine whether each distribution is a probability distribution. I'm going to zoom in a little bit. So this is my part A. I have 2, 4, 6, 8, 10. I don't know what x are, so I'm just looking at it as a distribution, as a probability distribution. What I'd like to notice is 0.3, 0.4, that's 0.7. I'm adding stuff up. Another one that's 0.8, another 2, that's 1, and when one more, that's over 1. So the answer is no. This is not a probability distribution because the sum of p of x does not equal to 1. Now my next one, I couldn't find little symbols, so I'm going to draw those in. This is actually different suits of cards. And, well, a couple of things going wrong. I have hearts that are listed twice, and maybe it's a typo. Yeah, I think there's a typo in the book, but I'll draw it like this. So I have the four different suits. This is not an actual probability of the cards, but if you try to add 0.4 and 0.2 and 2 of the 0.8, so this is a quarter, quarter and a quarter, that's a half. So in fact, this is a probability distribution. I have my outcomes on the top. I have my probabilities on the bottom. The probabilities do add up to a 1. The one thing that I'd like to mention about this one is the variable is not numeric. It is a categorical variable. So if you have categorical variables, it would be really hard to find numeric values like mean and a standard deviation, median, and all that other stuff that we learned in chapter 3. So what we're going to do is distributions like this aren't going to show up in our class just because we can't do anything about them except draw a histogram. So this is my part C. This is the distribution of boys versus girls in a family of 2 kids. And this is, in fact, a complete distribution of what possibly could happen. So you have either a boy or boy. You either have a boy and then a girl, girl and then a boy, or 2 girls. So the probability of each event happening is a quarter. This is a very good description of a probability distribution, which actually makes sense. Now, part D, I'm just going to outline this number right here. As soon as you see a negative 0.6 as a probability distribution, just say no. The probability of 3 is less than 0. You can't possibly have that, so that does the trick.